All right. So now we're going to, let me see if I can find my document here. I'm going to be working on the problems at the end of that review sheet that I gave in class. So I think we've done a pretty good job up through question 26. And then I started skipping around. So I wanted to start with number 27. So this is the end of the review page that I passed out that had like 38 questions on it or so. All right, so on 27, it says, in one country, it was observed that 59 out of every 100 births is a baby with brown eyes. Okay, so the probability of having a baby with brown eyes would be 59 out of 100. And then it's asking, okay, so in 660 births, how many brown-eyed babies would you expect? So for every 100, you're going to have 59. You've got over 600. So you know for each 100, you're going to have 59. But then you have that 60, that extra little 60 you have to figure out. Okay, the simplest way to do it is just to take the probability times the 660, and that'll tell you the expected number of brown-eyed babies. Okay, so let me do that while you do that. Take 660 times the 59 and then divide by 100, and you get 389.4, so about 389 brown-eyed babies. Okay. All right, so let's look at question number 28. All right, that question says a fair die is rolled, and you want the probability of rolling an odd number or a number less than 3. So I had one of these on the selected problems off of the quizzes. So let's just look at our outcomes. Odd number would be 1, 3, or 5. A number less than 3 would be 1 or 2, but you don't want to double count. 1 is odd and less than 3. You don't count it twice. So you have 1, 2, 3, 4 distinct outcomes out of the 6, and that gives you 2/3 on that. Okay. All right, and then on question number 29, a card is going to be drawn from a deck of 52 cards, standard deck. What's the probability of drawing a face card or a 5? So there's 12 face cards, jacks, queens, and kings. Okay. Out of the 52. And since it says or a 5, I could think about how, and there's 4 5s. Okay, so that would give me 16 out of 52. And when I simplify that, let's see. All right, 4 goes into 16. 4 times 4 goes into 52, 13 times. So that would be the answer to the first question, drawing a face card or a 5. Either a face card, you could be a face card, you could be a 5, or you could be both. And then it says, what about a face card or a club? And I threw that extra question in there because when you're doing that one, there's a probability of 12 out of 52 getting a face card. Club, that's one of the suits. There's 13 out of 52 clubs. So you might think the answer is 25 out of 52. But the problem is, isn't there a jack, queen, and king of clubs? You would have counted it twice because you would have counted it as a face card and counted it as a club. So you have to subtract those 3 cards, which would be the jack, the queen, and the king of clubs. You don't want to double count them. So if you don't have the list of cards in front of you and you're using the formula, don't forget not to double count. So that would turn out to be 22 out of 52, or 11 out of 26 would be the answer to the second part here. Okay. All right. I'm going to go ahead back to the original document and just snip the new page. If I can find the original. Where is it? downloaded it. There it is. Let me scroll down a little bit. I can't write on a PDF. I have to actually take a picture of it before I can write on it. I'll get that up a little bit higher. All right, let me try that again. Go back here. I'm going to do this snip and sketch. There we go. Okay. All right, so now I'm still working on those problems off the review page. Number 30 says a family is selected at random from the city, and we want the probability that the size of the family is less than 5. And the chart that you see has the family size with the probabilities, okay, that were determined empirically, right? So less than 5, that means it can't be 5. So you would just add up these, take the 0.455, the 0.212, and the 0.197, and add those three together. 0.455 plus 0.212 plus 0.197, and that gives us 0.864. So there's an 86.4% chance that the size of the family would be less than 5, which would be either 4 kids, 3 kids, 2 kids. Okay. And it said round to 3 decimal places, but it actually turned out to be 3 decimal places. All right. Now, 31. This question actually is pretty common, this type of thing. A lot of times when you manufacture stuff, there's a quality control group that keeps track of like how many failures there are, how many defective items there are. So like say it's batteries, so in a batch of 100 batteries, maybe 2 are defective. So they'll do samples like that periodically to kind of keep up with keep improving their quality. So what we know is 5 apples in a barrel of 25 are rotten. So there's a 5 out of 25 chance that your apple's going to be rotten, which is 1 out of 5. And then it says, what's the expected number of rotten apples you would have if the sample were 2? Now, I think it makes it hard that it's so few, because it's more this idea, like if the sample were 1,000. So like if you were Barber's Orchards, that's a place we go to all the time to get apples. If you were Barber's Orchards, and we're talking about, 1,000 apples, then how many of those 1,000 would you expect to be rotten? It would be easier for you to understand. But what you would do is you would take the probability of having a rotten apple times the number of apples. This is just like the brown-eyed baby problem. You'd multiply those two. It just is weird because what you're winding up is that 2/5 of an apple would be rotten. Where if that had been like 200 apples, it would have been 200 divided by 5. Okay, so it would have been like 40 apples would have been rotten. All right, so let me try to get these other 2 knocked out. So question number 32, you got this contractor. He's considering a sale that promises a profit of $31,000 with a probability of 0.7, or a loss of $10,000 with a probability of 0.3, and you want the expected profit. So you take your profit of $31,000 times the probability, which is 0.7, plus the profit, which is actually a loss. Let me just go ahead and do minus 10,000 with a probability of 0.3. So I'm doing 31,000 times 0.7 minus 10,000 times 0.3, and I wind up with an expected profit of 18,700. Okay. All right, then 33 is a lot like 32. So with 33, contractor's trying to pick between these 2 projects, and it's trying to use expected value to do that. So you do what we did on 32, but you do it for project A, then you do that for project B. I think I might be able to squeeze it in up here. So 50,000, probability of 0.6, okay, plus 88,000, plus, not plus, times the probability of that, which is 0.3, and then plus $10,000, and the probability of that would be 0.1. Okay, so I'm going to multiply those out. Let me try to do that carefully so I get the right number. 50,000 times 0.6 plus 88,000 times 0.3 plus 10,000 times 0.1. Okay, and that would turn out to be 57,400. Now, in here, it's like a word that's cut off. So if you get into your problem, make sure you're looking at whether it says profit, and then see here it says and a, but we don't see the word, and I'm not sure what it was originally. So I'm assuming it's profit, but maybe it was loss, or maybe you'll have loss when you get in there to do your problem. If it were the loss, I would have subtraction going on. Then with project B, I do the same thing. I'm going to take 100,000 times the probability of that happening, plus 63,000 times the probability of that happening, and then and A, and it doesn't say, so let's assume it's profit of 20,000, okay, with a probability of 0.2. But again, if the word had been loss, I would have subtracted 100,000 times 0.1 plus 63,000 times 0.7 plus 20,000 times 0.2. Okay, so for that one, I'd get pretty similar, 58,100. Oops, just 1. Okay, so the expected profit is what you're seeing there for each. So if you're going to base your decision on expected profit, you'd want the greatest possible. And so you would go with B. Okay. All right, there's a few more problems. Let me go in, see if I can go ahead and do it in one video so I can get through this a little more quickly. I think we just got a few more. Okay, so we just finished 33. We kind of jumped around real fast at the end, so I just wanted to take a moment to get these done. All right. Okay, so I may need some more room on a couple of these, but on 34, I think I can squeeze in there. All right, so on this one, we need the expected net winnings. Okay. All right, so they're going to raise money by raffling a trip that's worth $500. 3,000 tickets are sold for $1 each. Okay, so if the person who's buying the ticket has a 1 out of 3,000 chance, or the probability of 1 over 3,000 of being a winner. Okay. All right, and the winnings are worth 500. So that turns out to be 500 over 3,000, which you can do on your calculator. Simplify that, you'll get a 1/6. And let me change that into money, into dollars by dividing that. And I get point. So that equals about, and that would be 0.166, keeps going like that. So about 0.17 if I round to 2 decimal places. Okay. All right, now that's not my net winnings. That would just be the expected payout. The expected winnings would be 0.17. But then I had to buy the ticket, and it cost me $1. So my net winnings would be to take my payout but take away from that the $1 that I had to pay. And when you do the 1 minus the 0.17, that gives you a negative 0.83. Okay, so my expected net winnings would be to lose 83 cents. Okay, and that's all they asked you for on that one. Okay, the net winnings would be to lose 83 cents. So that's not really a fair situation. You're paying too much to play that game, right? And then sometimes they ask questions like, what is the profit that the charitable organization would make? And that's going to depend upon whether that thing they're raffling off was donated or not. So, they had 3,000 tickets they sold at $1 each. So that would be $3,000 in revenue if all the tickets were sold. All right, so that would be their profit if the trip was donated. If it wasn't, then they had to pay the cost of that trip. And so then $2,500 would be the profit for the charitable organization. Now, that's not this question. That was just me throwing in a what if question. Okay. All right. So now the next one says you're going to roll a die. You have these options when you do that. You're going to get $5 when you roll a 4 or a 6, and nothing for anything else. Okay. And the probability of each of those is a sixth. So our expected, we would multiply, not that, we would multiply a sixth. So the probability on each of those would be a 1 out of 6 chance, right? I don't want to write it there either. So I would do 5 times a sixth plus 5 times another sixth. And that would wind up giving me 5 6 plus 5 6 is 10 sixths. And 10 divided by 6 turns out to be about 1.67. Now, that's not my net winnings. That 1.67 would be my expected payoff. Okay. All right, because I get a 5 for rolling a 4 or a 6, but I don't get anything for any of the others. So that 167, take away the $3 I paid to do it. So 1.67 take away 3 means the net winnings would be a negative $1.33. Not a fair game. Okay. It's unfair against me. Okay. All right. Now, number 36, that's one where you're tossing 3 fair coins. All right. So we had all those possibilities. I'm going to need a little room on this one, but let me just see if I can write it, do a systematic listing. And I'm going to use this space down here. Okay. So I could have 3 heads. Okay. 2 heads and a tail. Kind of get all my possibilities listed. We did it earlier, but I just need it right here. Okay, so I have those 8 possibilities. So I'm working with getting heads. So I could have, let my variable be the number of heads. There might be 0 heads, 1 head, 2 head, or 3 heads. No heads is 1 out of the 8. 1 head would be 1, 2, 3 out of the 8. 2 heads would be 1, 2, another 3 out of 8. And then all 3 heads would be just the 1 out of 8. Okay. All right. So now here's what happens on this one. You get 27 cents if you get 3 heads. So your payout would be 27 cents. Let me just do it as cents. So not the decimal. Let me just do 27 cents. Okay. For 2 heads, I get 15 cents. So I'm going to multiply by 15 cents. For 1 head, I get 8 cents. Okay. And then what I'm going to do is I'm going to multiply those together. So that would be 24 eighths. That would be 45 eighths. And that would be 27 eighths. And those could be simplified, but those are no one of those is my final answer. I need to add all those up. So I get 24, 27 would be 51. That would be 96 eighths, which turns out to be 12. So the expected payout would be 12. Okay. And if I want this to be a fair game, then I should charge 12 cents. So charge 12 cents to play. Let me do it with cents. Charge 12 cents to play. And then your expected payoff would be 12 cents. And so your net winnings would be 0, which is what it takes to be a fair game. All right. And then we just got a couple more. All right. And these already have the probability distribution table. So that saves you a little bit of time. So the X is the number of houses sold by a realtor in a single month at this real estate office. Okay. So 2 houses, probability he'd do that would be 12%. Probability he'd sell 5 houses would be 14%, and so on. So if you want to figure out the expected value of the number of houses sold by a realtor, you would multiply these together, get those values, okay, get what those are equal to, and then add all that up. But you really can just type all that in and then add it all up. So what I'm going to be doing, I'm not going to write it all out, is I'm going to be multiplying like that, then adding 1 times 0.01 and 2 times 0.12, 3 times, and continue like that. Okay, so take a moment to do that on your calculator. Let's see what we come up with. Plus 7, I'm down to 7, 21. Okay, and I wound up with 3.6. Okay, so the expected value for the number of houses that would be sold by that realtor would be 3.6 houses. Okay, so about 4 houses. All right, and do the same type of thing on this one. This is kind of like the number of absences problem. So on a particular day, there's a 4% chance that there'd be no complaints, or there's a 33% chance there would be 3 complaints. You want the expected number of complaints on any given day. So you're going to do 0 times 0.04 plus 1 times 0.11 plus 2 times 0.26, and so on till you get to 5 times 0.12. But you can type all that in on your calculator. Okay. You don't have to show me the individual things. Just be careful typing it in. It's plus 3 times 0.33 plus 4 times 0.19 plus 5 times 0.12. And I get a total of 2.98. So I could expect 2.98 complaints per day, so about 3 complaints a day on a given day. Okay. All right, so let me stop that. I'll get these videos posted.